Welcome to my tutoring session in A-level chemistry. In this video, I'll talk about the chromatographic separation technique. I'll begin the video with a brief introduction to the chromatographic separation technique. This will be followed by stationary phase and mobile phase used in chromatographic separation technique, principle involved in chromatographic separation technique and their applications. And later in the video, I'll discuss the polar and non-polar stationary phases used in chromatographic separation techniques. What is chromatography? Chromatography is a separation technique where the given multi-component mixture can be separated into its individual components using a stationary phase and a mobile phase. So both stationary phase as well as mobile phase are required for carrying out the separation of the given multi-component mixture into the individual components. Let's say, for example, we are given with a multi-component mixture S, and our goal or objective is to carry out the separation of this given multi-component mixture into its individual components A, B and C, and this can be accomplished using a stationary phase and a mobile phase. Now the stationary phase is usually a solid, like polar silica gel is used as the stationary phase, and the mobile phase is a liquid solvent. It is named mobile phase because it is a moving phase, and in case of stationary phase it is a non-moving phase, and hence the name stationary phase. So stationary phase is a non-moving phase while the mobile phase is a moving phase. Now let's carry out the separation of this given multi-component mixture into its individual components using stationary phase, that is solid silica gel, and mobile phase, that is hexane. So we'll be using silica gel as the stationary phase and hexane as the mobile phase for our separation. Now let's prepare the stationary phase. Now stationary phase can be prepared by mixing the silica gel powder in a low boiling solvents like dichloromethane, chloroform, diethyl ether, or even hexane can also be used. Now the prepared slurry is then coated as a thin layer over the glass plates of suitable dimension. The prepared plates is allowed to dry at room temperature, and then later it is placed in the oven for activation. It is placed in the oven for nearly 1 hour at a temperature of 100 to 120 degrees Celsius. Now these TLC plates can be prepared in the laboratory or they can be purchased. They are also commercially available. Now commercially available TLC plates are of two types. One is the glass backed TLC classical silica gel plate, which is available in different dimensions, and the other is the silica gel coated as thin layer over polyester sheets. Now the advantage with the pre-coated polyester sheets with silica gel is that it can be easily cut using scissors, and moreover it can be rolled to fit into a chromatographic chamber. Now the thickness of the silica gel layer, it varies. For analytical plates, the thickness of the silica gel slurry is around 0.25 millimeters, while for preparative plates, the thickness varies from zero point 0.5 to 1 millimeter. Now, in case of column chromatography, the prepared silica gel slurry is filled into the glass column, and the column of stationary phase of silica gel slurry acts as a stationary phase. Now, the column of silica gel slurry acts as a stationary phase, which is supported by the glass column. So, stationary phase is a solid on a solid support. In case of thin layer chromatography, the solid is the silica gel layer and the solid support is the glass plate. While in case of column chromatography, the stationary phase is the silica gel slurry while the solid support is the glass column. So overall, a stationary phase is a solid on a solid support. In case of high pressure liquid chromatography columns, they are available in stainless steel materials of different dimensions. Well, in case of columns for gas chromatography, they are in the form of coils, and the material is usually stainless steel, copper, or in some cases it is glass. So glass material is used when the material that is used for separation or the substance that is being separated interacts with the either stainless steel or copper material. In such cases, inert material like glass columns also used. Now let me explain the separation of the multi-component mixture S into its individual components A, B and C by considering thin layer chromatographic method as a representative technique. Now the given multi-component mixture is made up of three components A, B and C. Now you have to take a TLC plate, draw a baseline at the lower end of the TLC plate, and over the baseline that is drawn using pencil, you have to mark a spot. So mark a spot on the baseline that is drawn over which you will be applying the sample. Now the sample can be applied using micro syringes, micro pipettes, capillary tubes, or even droppers can also be used. But the most efficient way of applying the sample on the baseline is by using micro syringes. Because using micro syringes, you can control the addition. Apply the sample on the baseline using micro syringe. Dry the spot. And before you place it in the TLC chamber, the TLC chamber should be filled with the solvent. Close the chamber and set it aside for saturation. And after the saturation period, you introduce the TLC plate into the chamber. When you are introducing the TLC plate into the chamber, the most important thing to be borne in mind is to make sure that the solvent level is below the baseline. Now here in this diagram, you can see that the solvent level is above the baseline. So when this happens, the sample applied over the baseline, it dissolves into the solvent system and there will be no separation. So the correct way is to introduce the TLC plate into the chamber, making sure that the level of the solvent is below the baseline where the sample is applied. So this is the right way of preparing the TLC plate and introducing the TLC chamber. And during the development process, you can see that the solvent front, that is hexane, we are using hexane as the mobile phase here. So gradually the hexane, it flows to the stationary phase by capillary action. And as the solvent front travels to the stationary phase, the components of the given sample mixture, it gets separated into individual components A, B, and C. So the components in the given multi-component mixture, they get separated as they move through the stationary phase. So separation takes place depending on the relative affinities of the components towards the stationary phase. So the component which has greater affinity towards the stationary phase travels slower, while the components with lesser affinity towards the stationary phase travels faster. So the speed with which the component travels to the stationary phase depends on the relative affinity of the components towards the stationary phase. So component A has less affinity towards the stationary phase, hence it travels faster, while component C, because of its greater affinity or attraction towards the stationary phase, it travels slower. So difference in the relative affinities of the components towards the stationary phase brings about the separation. Now in case of column chromatography, you fill the glass column with silica gel slurry, and later you introduce the sample and elute the column with the solvent that is selected for the separation, and gradually you can see the three components getting separated with time. So for carrying out the separation of the given multi-component mixture, you are using silica gel as the stationary phase and hexane as the mobile phase. Now hexane is a non-polar solvent. It is the mobile phase that is used for the separation. So it is named as mobile phase because it is a moving phase. It moves over the stationary phase. So stationary phase is a non-moving phase. It stay put, doesn't move. Now the stationary phase surface is highly polar. The surface of the silica gel is highly polar due to the presence of the polar silanol groups. So polarity is contributed by the polar OH groups, which when covalently bonded to the silane, it is called silanol groups. Now we are trying to separate three components A, B, and C of varying polarities. So one of the components highly polar, it is paracetamol. So paracetamol is a analgesic, it is a painkiller. So because of its high polarity, it travels at a slower rate, and it interacts with the stationary phase. So there are two types of non-covalent interactions between the sample, that is paracetamol, and the stationary phase as well as the mobile phase. So the sample, it interacts both with the stationary phase as well as the mobile phase. Now you can see that strong hydrogen bonding is formed between the polar silanol groups of the stationary phase as well as the polar groups of the sample, that is keto group as well as the hydroxy group. And van der Waals interaction or van der Waals forces between the non-polar hexane and the non-polar portion of the paracetamol molecule. So here the hydrogen bonding force is much stronger than the van der Waals forces, and therefore the molecule, the motion or the movement of molecule is brought down by this strong hydrogen bonding as well as weak van der Waals interaction with the nonpolar mobile phase. Now I have made separate videos on topics van der Waals forces and hydrogen bonding. Please take a moment to watch those videos as the videos will provide you with a better understanding of this video content. Now the second molecule is less polar as compared to paracetamol. It is acetophenone molecule and it travels over the surface of the stationary phase, that is silica gel, and it travels much faster than the polar paracetamol molecule because of its intermediate polarity. And again, you can find hydrogen bonding interaction with the keto group of the acetophenone, and it also interacts with the non-polar mobile phase hexane by van der Waals forces. So both van der Waals forces as well as hydrogen bonding, they control the movement of the acetophenone molecule, which is of intermediate polarity. Now third molecule is naphthalene, which is totally a non-polar molecule, and it travels faster over the polar stationary phase, and it interacts only with the non-polar mobile phase. So there is no interaction with the stationary phase because the stationary phase is polar in nature while the naphthalene molecule is non-polar in nature. So there is non-polar interaction via van der Waals forces between the non-polar naphthalene molecule as well as the non-polar mobile phase. So the mobile phase, it clings on to the molecule. The molecule interacts with the mobile phase strongly and therefore it is carried away by the mobile phase. And there is no interaction with the stationary phase. And for this particular TLC separation of these three molecules of varying polarity, stationary phase uses the silica gel and mobile phase is hexene. So let's apply these three components on the baseline of TLC plate with a polar stationary phase, that is silica gel layer. And after separation, you can see that component A, that is naphthalene, has covered a larger distance as compared to acetophenone and paracetamol. Now after the separation, make sure that you mark the distance traveled by the solvent front. And mark the distance traveled by the components naphthalene, acetophenone and paracetamol. So you have to mark the center of the spot. And this will be the baseline. So to calculate the distance now, you calculate the distance from the baseline, distance traveled by the solvent front hexane, and the distance traveled by the three components naphthalene, acetophenone and paracetamol by considering the center of the spot. So this is separation of three individual components, but our objective is to separate the given multi-component mixture into individual components. So apply the sample over the baseline and carry out the separation by TLC method. And later you calculate the distance traveled by the solvent as well as the individual components. Now the parameter that can be used for identification of compounds is the RF value. Now RF stands for retardation factor or retention factor. It is calculated by dividing the distance traveled by the compound by the distance traveled by the solvent from the baseline. Now this RF value is constant for a given compound and for a given combination of stationary and mobile phase, and therefore RF value can be used for qualitative analysis, that is for identification purpose. as the RF value is unique or constant for a given substance for a given combination of stationary and mobile phase. And that's how we have successfully carried out the separation of the given multi-component mixture into individual components A, B and C. So the components that we have separated are naphthalene A, acetophenone B and paracetamol C. Now there are two types of stationary phases. One is polar stationary phase, the other is the non-polar stationary phase. In normal phase chromatography, the stationary phase is polar, for example silica. In case of reverse phase chromatography, the stationary phase is non-polar, for example C8 and C18 columns. Now in a polar stationary phase, the silica surface is polar in nature due to the presence of silanol groups. Now this polar stationary phase can be converted into a non-polar stationary phase by adopting a technique called selenization. Now by this procedure, that is selenization, you can convert a polar stationary phase into a non-polar stationary phase. Now here in this case, we are treating silica layer with selenizing reagent dichlorodimethyl silane. So after the reaction, you can see that the polar silanol groups are completely blocked, making the polar surface non-polar. So by selenization technique, you can convert a polar stationary phase into a non-polar stationary phase. And you can vary the polarity of the stationary phase by using several selenizing reagents. Now when you treat the polar silica layer with octyl chlorosilane, you can prepare a C8 column. And you can prepare C18 column by treating the polar silica layer with octadecyl chlorosilane. So why they are called as C8 and C18 columns? It is based on the number of carbons in the aliphatic chain. In case of C8 column, you find it is a 8 carbon chain, while in case of C18 column, you find it is a 18 column chain. So they are named after the number of carbon atoms that are present in the aliphatic chain. Now C18 column, it has more number of carbon atoms and hence it is more hydrophobic than the C8 column. Now C8 column is less hydrophobic as compared to the C18 column because of fewer number of carbon atoms in the aliphatic chain. Now both C8 and C18 are reverse phase columns suitable for analyzing weakly polar substances. So C8 is a silica bonded octyl group, while C18 is a silica bonded octadecyl group. So alkane bonded to silica with an 18 carbon chain in case of C18 column and 8 carbon chain in case of C8, that is octyl. And therefore C18 is more hydrophobic than C8 chromatographic column. Now in chromatography, stationary phase and mobile phase are the two essential components that allow for the separation of substances in a mixture. Now stationary phase, it is a non-moving phase. In chromatography, the stationary phase plays a crucial role as a fixed material as it does not move and facilitates the separation process. When using a polar stationary phase such as silica gel or alumina, its polar surface effectively attracts polar molecules. Now, this interaction enhances the separation efficiency by allowing for more precise identification and isolation of components based on their polarity. Now, a stationary phase is usually a solid or a liquid coated on a solid support. it holds or interacts the components of the mixture as they pass through. Now, as you have seen in the experiment that you have performed, paracetamol interacts effectively with the stationary phase, and therefore it is folded back and it travels a lesser distance. Now, different components are retained for different lengths of time based on how strongly they interact with the stationary phase. You can see that naphthalene interacts weakly and therefore it is less retained and hence it travels faster. Examples: silica gel in TLC or column packing in gas chromatography. And what about mobile phase? The mobile phase is a moving phase. It's always in motion during the development process. Now, it can be a liquid in case of liquid chromatography like paper, TLC and column chromatography, or it could be even a gas. Now, mobile phase can be a liquid or a gas. So it is gas in case of gas chromatography. It carries the mixture through or across the stationary phase. Now, components that interact weakly with the stationary phase move faster and elute earlier. Like in case of naphthalene. So naphthalene interacts, there is no interaction with the polar stationary phase, and therefore naphthalene moves faster and elutes earlier if it is a column chromatography. Now, there are two types of separation techniques. One is normal phase chromatography, other is the reverse phase chromatography. Now, the explanation that I given for carrying out the separation of the multi-component mixture A, B and C is purely based on normal phase chromatography. Where the stationary phase was polar, we have used silica gel. Mobile phase is non-polar, we have used hexene. And polarity trend was that polar compounds are retained longer. Like paracetamol is a polar molecule, it was retained for a longer time. It travels slower. Example, you can find normal phase chromatographic technique in case of TLC and column chromatography. And what about reverse phase chromatography? Now, reverse phase chromatography is just the opposite to that of normal phase chromatography. So, in case of reverse phase, the stationary phase is non-polar. For example, C8 and C18 columns, which I have just explained, and mobile phase is polar, like water and methanol. So, polarity trend is non-polar compounds are retained longer. An example will be the classical high performance liquid chromatographic method. Now, what is the principle of separation? Now, the basis for all the chromatographic techniques is the partition or distribution coefficient of the sample between the stationary phase and the mobile phase. Now, the sample during the separation process, irrespective of the chromatographic technique that is being adopted, the sample, it is sandwiched between the stationary phase and the mobile phase. So, if it interacts more strongly with the stationary phase, it will be retained. It will travel slower. If it interacts strongly with the mobile phase, it will travel faster. And some of the important applications of chromatographic separation technique is that it can be used for separation and identification of analgesics, antibiotics, amines, amino acids, alkaloids, glycosides, sugars, vitamins, and many pharmaceutical drugs. And it can also be used for detection of impurities. Both qualitative as well as quantitative analysis can be performed using chromatographic separation technique. Now, based on the principle of separation, chromatographic technique can be classified as adsorption chromatography and partition chromatography. Now, the explanation that I given for carrying out the separation of three components is based on adsorption chromatography, where the separation is based on adsorption on the surface of the solid stationary phase. Examples for adsorption chromatography are TLC, column chromatography, and HPLC. And the other type is the partition chromatography, where the separation is based on partition between two immiscible liquids. Partition of what? Partition of the sample being separated between the stationary phase and the mobile phase. So in case of partition chromatography, both stationary phase as well as the mobile phase both are liquid in nature. Examples are paper chromatography and gas liquid chromatography. In my forthcoming videos, I'll be giving a detailed explanation about each chromatographic technique. I'll be making separate videos on each technique like paper chromatography, thin layer chromatography, column chromatography, HPLC, and gas chromatographic technique. So please watch out for those videos. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.